Okay, the previous case we mentioned that is actually a special case where we have multiple measurements at each distinct value of x, and our x is discrete in that case. And now we will talk about what if the our x variable is continuous. So we want to calculate the weighted least squares when our x is continuous, and we know there is a non-constant variance issue for the error. Again, consider the simple linear regression model we have, the same one from before, and also we assume this EI have mean 0, but now with variance sigma square over WI. So we want to adjust the problem that it has unequal variance because we use this WI. And now we want to kind of get it, make a transformation by multiplying both sides of this equation by square root of WI. See, we multiply each of the elements by this quantity, and now our error term, transformed error term, becomes this, and it has mean 0, but now with variance sigma square. Now it has constant variance, right, after this transformation. And with that transformation, we can now calculate the least square estimate for this new model, the transformed model. And let's get our corresponding new y and new x. Actually, we have two x here. So our new y is like this. And this is our new x1 and our new x2. And we just rewrite it like this if we go back. So this is our new x1 and this is our new x2, right? And now we rewrite our model like this. This looks kind of familiar, right? But it has more than one predictor. So this is kind of this is actually a multiple linear regression, to be honest. But I think I mentioned this before. With this formula, it works for both simple linear regression and multiple linear regression. So we can use this formula. This is our old formula for simple linear regression, but with this new values for X matrix. So this X matrix would have a column for X new 1 and a column for X new 2, but there isn't a column of 1, just like in simple linear regression model. So yeah, but you can use this formula to do the estimate in this new model for beta 0 and beta 1. So let's just do the comparison here. We have one model with this weighted least square being like this, and we know this EI have weighted error variance. And the second one is a least square model, but with this like transformed format. So in this one, we know that if EI is like this, and then after we do the transformation, we have make the error variance constant. So this is kind of the link between the weighted least square and the least square. We can use the least square model to find the weighted least square model. So which is basically fit the weighted least square on 1 as equivalent to fitting the least square on 2, which is a multiple linear regression with 2 predictors and no intercept. Okay, and I have an example here where when we have a continuous x, and suppose we know that the sigma I square, sigma square I, anyway, is proportional to xi. So that is the variance of ei being like this. This is what I mean by proportional to this xi. So now we could take this weight wi as 1 over xi. So after we take this weight, the variance of the square root of wi times ei is like this. And if we calculate this variance, it's this x. So this coefficient we have to take a square of it before you can times the variance of this ei. Like we take the square of it, it's 1 over xi, and the variance of ei, is this. So this xi canceled, we have this variance being constant after we transform this ei, right? And now, so when you have this wi, you can also use the weighted least square formula like this to get your estimate of beta 0 and beta 1. So these two are equivalent. So this one you will need to get the value of wi. Yeah, you can also use this formula. Well, I think we actually have talked about this, but let's take a look. I'll have this data set post on Blackboard, and we do the transformation and get a new model to fit. And we want to compare this regression results with the weighted least square regression. And compare the fits and prediction intervals. Well, let's do the prediction interval and also take a look at the comparison again. Yeah. Let me see. Okay, here we go. So this is the cleaning weighted data again. We have run through this. So I mentioned this is how you could manually do a weighted least square, but now it's clear it's actually a least square version of a transformed model. So we have transformed this y, and we have transformed our x. Well, it becomes our x new, the x2 new, and this becomes our x1, the new x1. And we have to remove the intercept because we have no more intercept in this multiple linear regression. It already got x1, x2, and no intercept. So yeah, let's do this. Do the summary. Again, this is the same. The estimates are the same as this first least square model. Right, transform the model and the original model that was weighted least square estimation. Yeah, this is the plot again, and also this is when you do a prediction. So let's do a prediction when we know x equal to 16, and we have to provide the weight for it. The weight is 12. If you look at the data. And we have a summary of the standard deviation for each distinct value of x. And if we do this prediction, we can do predict with this linear model provided, and the new data is here. And now we have to transform it back to the original room number. If you do this prediction predictor function here directly, what you get is this value, right? The transform value. You have to multiply the standard deviation back to it in order to get the room number. So this is your prediction. Yeah, so this is the tricky part. Just do not forget to on transform this y after this your